Look at this solar system model. The green ring is the habitable zone, where a planet receives exactly enough energy to keep surface water liquid. This model creates a deceptive illusion. Finding an exoplanet neatly inside it doesn't guarantee it can support life. Let's test that assumption. What happens if we replace our current sun with some of the most extreme stars in the universe, and then magically move Earth's orbit perfectly into their habitable zones to maintain our current temperature? As it turns out, dialing in the right temperature is the easy part. Moving the Earth uncovers a hidden set of astrophysical rules that dictate whether a planet thrives or dies. We'll start with Alpha Centauri b. It's a slightly smaller star that outputs only half the solar energy we're used to. If Earth stayed exactly where it is right now, global temperatures would crash to -70 degrees Fahrenheit. Within just a few weeks, a runaway deep freeze would quickly bury the continents in snow and freeze the oceans solid. To thaw the ice, we move Earth closer to the star. But this orbital chart illustrates the trade-off. Because we're closer to a star with less mass, orbital physics requires Earth to move much faster to stay in orbit. Our 365-day year shrinks to 225 days. This accelerated year creates a biological crisis. Because winter arrives 140 days early, traditional crops can't reach maturity before the first frost. Combined with a shift in the light's color toward redder wavelengths, which our crops aren't evolved to process, global food supplies would face an immediate, catastrophic deficit. The Kepler-16 system presents an even more extreme case. It is a binary pair, two incredibly dim stars that put out barely 15% of our sun's light. To keep Earth warm here, we have to push our orbit all the way inward to the distance of Mercury. This diagram reveals the consequence of that tight orbit. A planet orbiting two stars must stay far enough away to avoid their gravitational tug-of-war. By moving Earth closer to stay warm, we place it right inside the danger zone. Every 41 days, the massive, shifting gravity of the two stars would violently yank on our planet, eventually either ripping Earth apart or slingshotting it out into the deep space void. Orbital mechanics make the habitable zone of a weak star a trap. You either freeze in outer orbits, face complete global agricultural failure, or get torn to pieces. On the other side of the spectrum is Procyon A, a searing star that pumps out 7 times more energy than our sun. At our current distance, the global average temperature would shoot to nearly 300 degrees. The oceans would physically boil over, trapping all the heat and turning the planet into a super-pressurized Venus-like hellscape. To cool things down, we push Earth far outward to the asteroid belt. The temperature stabilizes, but the light itself remains lethal. Procyon A burns extremely hot, blasting out massive amounts of ultraviolet radiation that instantly shreds our ozone layer and causes catastrophic cellular damage to anything exposed. Procyon also has a white dwarf partner. Every few decades, this secondary star swings close, violently warping our orbit and dragging the planet into erratic ice ages followed by intense hothouse periods. If we move Earth around a dim red dwarf like Proxima Centauri, we have to maintain an incredibly tight 8-day orbit to survive. Look at this model. At this range, the star's gravity acts as a brake on Earth's spin until it becomes tidally locked. The planet splits into a permanent scorched desert dayside and a permanent nightside trapped in ice. Living in the narrow twilight zone between those halves offers no safety. Proxima Centauri is a volatile flare star. Without warning, its intense magnetic fields violently erupt, completely bombarding the planet with massive, lethal doses of high-energy X-rays and extreme ultraviolet radiation. Over thousands of years, these relentless superflares act as a physical abrasive, slowly bleeding Earth's atmosphere out into the vacuum of space until the planet is a naked rock. A planet's temperature is a secondary concern if its star's light spectrum blinds the wildlife and its magnetic field strips away the air. In the future, our own sun will swell into a massive red giant, up to 300 times its size. A towering wall of orange plasma would consume the entire sky, instantly flash boiling the oceans and rapidly melting the continents into a sea of magma. To escape incineration, we have to push Earth past the orbit of Pluto. the temperature eventually drops to a barely survivable level. But a single orbit out there takes over 300 Earth years. Entire generations would be born, live, and die entirely within a century-long winter. Watch the habitable zone ring on this map. As the red giant brightens, the zone of liquid water sweeps outward toward Jupiter and Saturn. The thick ice shells of moons like Europa and Enceladus would melt entirely, rapidly transforming them into tropical water worlds that could potentially support alien life. The most extreme case is the Vela pulsar, the crushed core of a supernova rotating 11 times a second. It blasts out a relentless cosmic strobe light of pure ionizing radiation that acts as a repeating EMP, frying electrical grids and shredding DNA instantly. Moving closer to a pulsar to get warm only subjects the planet to a gamma-ray cannon. Even worse, the gravitational pull of such a dense point mass would trigger global magnitude 10 earthquakes, shattering the Earth's crust from the inside out. Dead and dying stars don't have habitable zones. They only offer varying distances of execution. Returning our standard yellow dwarf sun to the center of the solar system reveals that it is far more than a simple heater. It is a highly precise biological engine. A planet requires a host star with exact mass to maintain stable orbits, a stable lifespan to allow evolution to take hold, a predictable light spectrum, and a gentle magnetic field that leaves the atmosphere intact. The stability of life on our planet is a product of this exact pairing, a temperate orbit around a uniquely calm yellow dwarf. Identifying a planet in a habitable zone is only the first variable in a much more complex equation. Until we account for the behavior of the star it calls home, the location is an incomplete data point.